Good afternoon. Tomorrow we will speak about the head transfer two-dimensional steady-state problem. The governing equation is the following. You can see here. I want to make a remark. This is the steady state problem for head transfer. In fact, we don't have right the unsteady term. The boundary condition, similarly to which we have speak about in the video of the general equation, are 1, 2, and 3, where S1, S2, S3 are S1 the boundary on which temperature is specified, S2 where the head flux is specified, and S3 where the convection takes place. Now we will derive the equation for a generic element E, in which 1, 2, and 3 are the local node number. E, J, and K are the global node number. Global node number and are when we have more of more elements, and xi, ypsilon xk, ypsilon and xj, ypsilon are simply the coordinates of the 3-point. Now we will write the solution. The finite element solution of this problem can be obtained as: step 1. Idealize the solution region with triangular elements, but also we can develop for other triangular other than triangular, for example quadriangular or something else. This is an example of the discretization of the domain in of the entire domain or in triangular elements. Step 2. Assume linear variation of temperature. T refer E, superscript E means refer to element E, inside the finite element. We can also assume quadratic, cubic, or other kind of variation inside the element in this case, but the calculation complicates a lot. However, it's possible, I have done it. For example, the distribution function of x and epsilon can be written as alpha 1 plus alpha 2 x plus alpha 3 epsilon, that is equal to vector n multiplied the vector te. Step 3 is the derivation of the matrices. We have above we speak about the vector n. The vector n is the following for a triangular element: ni and j and k, and this is our the expression. And te is equal to T, the temperature at node E, Tj, the temperature at node J, and Tk, the temperature at node K. The expressions for AI, Bi, and Ci and Ae are the following, and Ae is equal to an alpha of this determinant. Now recalls the expression from previous video in which we have developed the general 3D finite element equations using Galerkin approach to solve the head transfer problem. The first matrix is K1 of the element E, and this equation is equal to that I have showed in the previous video. The only difference is the subscript M, and then there was E and J. Then we have K2 and K3, but as we have said, K3 will not be present because this is a steady state problem. M and N are E, J, and K globally, or 1, 2, 3 if we consider only the element E locally. Also, as we have said in the previous video, the vector PE is equal to P1E minus P2E plus P3E, where P1E, P23 and P3E are the following. Now we pass to the next page where we can see P3E. Okay, this is P3E in this part. Now we can state expressions for K1E, K2E, and K3E and PE using matrix notation. That is more simply to deal with. The first is K1, then we have K2, K3, and PE. But N, as we have stated before, are N, I, N, J, and K, and if we have more nodes than P, but in this case we have only these three, and only three nodes inside the element, so we have only these first three terms. Locally, we can renumber as N1, N2, and 3. P is the number of nodes in element E in local, and P superscript 1 is number of nodes in element E globally. Now, the matrix B is the matrix we obtain derivating n1 and 2 and p respect to x, n1 and 2 respect to y, and n1 and 2 and p respect to zeta. And D is this matrix. At the same, we can speak about P1, P2, and P3. These are the expression related to 3D quantity. But we have to remember that for a 2-3 triangular element with linear variation, we have that B is only a part of the matrix. We have no the zeta coordinate. So we have Ni, Nj, and Nk. Is a 2 multiplied 3 matrix. At the same is for D, is a 2 multiplied 2 matrix with only ky, kx, ky, k0 and 0 here. Now we have to recall what we have said before, that Ni, function of x and y, is equal to this quantity here. So, if we take derivative, we can calculate the following quantity here. Similarly, we can calculate nj, the derivative respect to x of nj, and the derivative respect to x of nk, and the derivative of nj respect to y, and the derivative of nk respect to y. And so, after doing that, matrix B for this problem became this quantity, this matrix fundamentally. So we can write the equation that we have stated before for K1 is equal to this quantity here. We have to perform some matrix calculation, we have to perform some simplification. For example, in a two-dimensional problem, we can write the differential dv equal to t multiplied dA, with t the thickness of the plate. If we assume uniform thickness, inside the element, but we can also simplify further and putting t equal to 1. Before calculate kx and ky multiplied this matrix. The result must have a 2 multiplied 3 matrix, and this is the result. Now multiply the first matrix for the matrix we have obtained, and this is the product. The result must be a 3 multiplied 3 matrix. So K1 can be written in this way. Before here and after multiplication, we can see the final result for K1. After the simplification, because here are all constant, these are all constant, so the integral over SE in dE we can put this matrix outside the integral, and so the integral of C over D is AE. And then the result must be multiplied for this matrix itself. As concern K2, K2 is equal to H, or the transpose of n, for n over S3, the integral over S3, the S3. If we consider constant over S3 H, we can put inside outside the integral. The surface S3 that experience connection must be known. What means? For example, let Ej of element E lie on boundary S3, so that nk is equal to 0, obviously. For the construction of nk, if we are here on the segment Ej, nk is equal to 0, but at the same time, if we are on ek, nj is equal to 0. Here, without loss of generality, we have chosen to stay on Ej. So we can write the expression of K2E that is equal to H integral over S3 E of this matrix. These matrices are obtained multiplying the transpose of n for n. To evaluate this integral, we can use area or triangular coordinates. We will do a lesson dedicated to it. But for now, follow me without the explanation. Because temperature is assumed to vary linearly inside the element, we can write that Ni is equal to L1, Nj is equal to L2, Nk is equal to L3. But along edge Ej, Nk is equal to 0. So L3 is equal to 0. We can therefore write the same expression as before, but with the L1 in place of n, with L1, L2, etc. in place of n. Now we have transformed an area integral, a surface integral, in a linear integral, in a line integral. How we have done this? Writing that the S3 is equal to T multiplied the S. The S is the line differential. And this is the domain. S equal to Sj and S equal to Se. Assuming constant thickness, we can write here the result. And now we have to use this formula. I have not the demonstration, the proof, but believe me, it's true. Someone else has proved it. Has proved it. This is the formula we will use now. For example, performing element-wise integration of the element of the matrix, we obtain, for example, in the 1, 1 position of the matrix, this is the integral we have to perform. The L is the same as the S. So, using this formula, we have this result. That is 2, this fraction 2 over 6. This is 1/3. At the same time, we can perform the integration of L1 of another element of the matrix, that is L1 multiplied L2. This is the calculation, and this is the result. So, if we perform all the integration of the matrix, element-wise integration of the matrix, we can obtain this result here. And we are done also for K2 of the element E. Now let's calculate P1E, and we perform the same calculation, but now we use the same triangular coordinates, so we can substitute n with L. But here we are an integral over a volume. We can simplify to an integral over an area, not over a line as before. So the formula we have used before is slightly different. This is the formula we will use now. For example, we can calculate the integral of L1 over the area AE alpha is equal to 0, beta is equal to 0, and gamma is equal to 0. Alpha is equal to 1. Performing the calculation as here, as stated here, we obtain 1/3. Similarly, we can perform the calculation over L2 and L3, and this is P1. This is the expression for P1. Now we can calculate P2e. The integral P2e, that is stated here, depends on the edge that lies on the het flux boundary, obviously. If the edge EJ lies on S2, NK is equal to L3 is equal to 0. And we also S2 is equal to thickness multiplied the line integral differential. So we can perform the calculation of P2. P2 is equal to Q multiplied T multiplied SEJ, that is simply the distance of V from J multiplied for this vector 1, 1, 0. Similarly, we can obtain P3 related to element E. We performed the same kind of integration. Obviously, if the edge EJ lies on S3. If is another segment, we have to modify slightly the expression, because as we have spoken before. Note, if the het flux Q or the convection het transfer term H occurs from two sides of the triangle element E, then the surface integral becomes a sum of the integral of each side. This is very important. Now we can go through the step 4. The step 4 states that the Semblet equation can be expressed as the matrix K multiplied the vector T equal to P. You can see a tilde here. That means that we are not speaking about the element, but the overall equation in which we sum all the elements together. In fact, K is equal to this expression. Is the sum in which we have we sum all the elements together, and we get we obtain the overall matrix for this transfer problem. At the same time, we can obtain P tilde, that is equal to the sum from E equal to 1 to E. E is the overall number of elements in the mesh. And finally, the overall equation have to be solved after incorporating boundary condition. We are done. In some next video I will explain with example this kind of problem. See you.